Hello everyone, welcome to the course Data Structures. This is N. Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. Today we'll be discussing about the AVL tree introduction. Let us see the overview of today's session. Here we will be discussing about what is AVL tree and AVL tree rotations, and followed by some of the rules you need to remember for performing operations on AVL trees. Right? These things we are going to discuss in today's session. First of all, we will look into what is an AVL tree, right? AVL trees are nothing but it is a special kind of binary search trees. As we have discussed in the previous session that what is a binary search tree? Binary search tree is nothing but BST. BST should follow some conditions. That is, if you are going to have a root node, on the left of root node, all the node values should be lesser than the root node. On right hand side, all the node values should be greater than the root node. This condition has to be satisfied for binary search tree. Now, the same thing, why we are going for this AVL trees? The same thing we are representing for binary search trees, but why we need to use this AVL trees? In AVL trees, when I am trying to represent a binary search tree like this, in that case, there may not have balancing of the tree. That means, let us see, in AVL trees, height of left subtree and right subtree of every node must be -1 or 0 or 1. That means, we are going to find the height of every node. Based on that, in AVL trees, it has to satisfy the property of balancing. That means, height of left subtree and height of right subtree, for every node, it must be either -1, 0 or 1. These values we need to get. Other than that, if we are going to get, then in that particular case, we are going to say that the tree is not balanced. So, we need to balance it. How to balance it? All those conditions we will see later. And because of this balancing of the tree, we are going to name these AVL trees as self-balancing binary search trees. In binary search trees, we don't have the balancing of the tree. To balance the tree, we are going for the concept of AVL trees. Let us see the example here. Example of AVL tree. This is a tree which you are able to see, right, with so many nodes, and this is going to follow the BST or not. First, we are going to verify, right? This is the root node. On left of it, all the elements are smaller, and on the right of it, all the elements are greater than the root node. Now, whether this tree is balanced or not, we need to check, right? This is a binary search tree. The first condition is satisfied. And the other one is the difference between the height of left subtree and right subtree must be having these values, either -1, 0 or 1. For every node we need to check this, right? First, check for the first one. Suppose this is my leaf node. For this, I don't have any left and right subtrees. That's why this height of this one is 0. And for 11, it is also 0. Why? Because for leaf nodes, all the height will be 0. Now, coming to this 8, this is the left subtree and this is the right subtree, right? This is 1 minus 1. This is nothing but 0. Now, for this, I am having only one node. Left subtree is 1 and right subtree is 0. So that we are going to result in of this one, this particular node is 1. And coming to the root node, here I have two nodes. Either we need to check the height from root node to the leaf node, right? Because of that, the height of this one is 2. 2 minus this one is also 2. That is 0. That means here you are not getting the values more than -1, 0 or 1. That's why we can say that this is satisfying our AVL tree condition. That is, every node is having the values of -1, 0 or 1. Okay. These are the properties it has to satisfy to be a AVL tree. Now, you can check here. This is an AVL tree or not. We need to verify. Let us check this tree. For every node, we need to check. From the leaf node, I am going to consider. This is the leaf node. This is 0. And this is also leaf node. For this is also 0. This is also leaf node. For this is that balance factor is 0. Now, observe. Now, I am going to check for 4, this node. the left subtree is 1 and right subtree is 0. And for this particular node 5, here we have 2 minus we don't have any right subtree, that means it is 0. 2 minus 0 is nothing but 2. Here it is not getting the balance factor of minus 1, 0 or 1. Because of that, we can say it is not an AVL tree, right? This is one thing. And here if you can check for the complete node also, 4 minus 2. That means here for the root node, I am having 4 nodes. 4 minus this one right subtree is 2. 4 minus 2 is nothing but 2. From this way also we can say that it is not satisfying the property of our AVL tree. That's why this tree is not balanced. Now, in AVL tree, the balance factor is defined for every node. As we have seen in the previous example, for every node we need to find the balance factor. How we are going to find the balance factor and what are the values it should contain? The balance factor of every node is either 0 or 1 or minus 1. Only these 3 values it should have. If other than this, if you are going to get any value greater than 2 or 2 or greater than that or less than, that is minus 2 or something, in that particular case we need to perform some operations to make the tree to be balanced. Okay, and how to find the balance factor of a node? Height of its left subtree minus height of its right subtree, right? Based on this, you are going to find the balance factor of a tree. If you can see here, I am having 12, 5, suppose 17, right? Now, how I am going to find the balance factor for this tree? For this is the leaf node and this is the leaf node. Height of left subtree and right subtree we don't have, that's why its value is 0. And for 17, height of left and right subtree is 0. Because of that, 0 minus 0 is 0. And for this root node, height of left subtree, you have one node here, because of that 1 minus. Height of right subtree also 1, 1 minus 1, 0. It is having the balance factor of 0, so that this tree we can consider it as a balanced tree. Now, when we have this tree is unbalanced, in that particular case, we are going to perform some rotations. Here you can see what is a rotation. Rotation is nothing but it is a process of moving the nodes to make tree balanced. In the previous example also we have seen a tree is unbalanced because of the balance factor is more than the values which we have taken 0, minus 1 or 1. Above these values if you are going to have, we are going to consider it is not balanced. In that case, we are going to perform this rotation. And when you are going to see these rotations, there are 4 different kinds of rotations that can be possible. One is left rotation, the other one is right rotation, then left right rotation and right left rotation. These 4 rotations we are going to perform to make tree balanced. You can see the same 4 divisions based on 2 categories. One is single rotation and another one is double rotation. In single rotation, we have left rotation, that is LL rotation is nothing but the left rotation. Right rotation, RR rotation is nothing but the right rotation. And in double rotations, we are going to perform 2 rotations. One is left right rotation. 2 rotations we are going to do, so that we are going to name it as LR rotation. The other one is right left rotation, that means here also we are going to perform 2 rotations, that is RL rotation, right? Like this way, these rotations we are going to apply on our AVL trees. See the conditions, how we are going to perform these rotations for all the cases, all the 4 different rotations how we can perform. Cases on imbalancing and their balancing using rotation operations. If the tree is imbalanced, in that particular case, how we are going to make it balanced by doing rotations, right? Let us consider this is a tree with the nodes, right? Suppose I am going to take the same example. Let us see. I am going to have 1, right? This is the first node which I am going to be considered as the root node. If I am going to have the element 2, where I need to insert in the BST I need to be inserted on the right of 1. Why? Because 2 is greater than 1 value. That's why we need to insert. Initially, when I am going to insert a particular node, in that case itself, we need to check the balance factor for every node. Right? Here, when I am going to see for 1, after inserting 1, I am going to check the balance factor. The balance factor of 1 is 0. Why? Because you don't have the left subtree and right subtree. Because of that, the balance factor is 0. Now, I want to insert 2. Where I need to insert 2? I need to insert 2 on the right of this one. Right of the root node. Why? Because it is greater than 1 value. Right. Inserted. After inserting, now check the balance factor for each and every node. Now, the balance factor of 2 is 0. Why? Because you don't have left and right child for it. And balance factor for 1 is what? You don't have the left child, because of that, that is 0. And you have the right child because of -1. So, we are going to get the value as -1. Still, it is satisfying our balance factor. It can be of -1, no problem. Next, if I am going to insert one more node, suppose I want to insert 3. Where I need to insert 3? I am going to insert 3 on right of 2. Why? Because it is greater than 2 value, right? Now, check for the balance factor of every node. This will be 0. And this will be of this left part, you don't have any value. 0 minus 1, you are going to get -1. And this one is 2. That means 0 minus 2, you don't have the left part. That's why it is -2. Right? This is how the imbalance is happening. When you are getting this imbalance, when I am going to insert the element on this side, where we are inserting, this is RR. Right side we are inserting. Right? Because of this imbalancing of your tree, we are doing this based on right rotation. That's why we need to perform left rotation to make it balance. That's why we are going to apply LL rotation. Right? We are going to apply LL rotation to make this tree balanced. Now, observe how it will be balanced. Make the rotation left. When I am going to rotate it as the left, now rotate it. It will come down. 1 will come down. 2 will be your root node and 3 will be your right child. Now, you can check the balance factor for this. This will be 0, this will be 0 and this will also be 0. Right? Like this way, we are going to perform LL rotation. Because of insertion of new node on the right side, this tree is imbalancing. Because of that, we are going to perform the LL rotation. Okay, I hope you understand. Next, we will go for the next rotation. Consider the order of elements. The same thing. Here we are discussing with an example. Here we have 3, 2, 1. Consider these are the elements where we have given based on this constructed tree. Now, I am going to insert 3 as a root node. Find the left and right, that is balance factor based on left and right subtrees. Here you don't have any left and right subtrees, because of the balance factor is 0. Then insert one more node. What is the next node? You have 2. Where I need to insert? 2 is smaller than 3. So, we are going to insert on the left hand side. Again, check the balance factor. For this it is 0 and for this it is 1 minus 0 is nothing but 1. Next, I am going to insert 1. Insert 1, it is lesser than 2. So that we are going to insert here. Right? Now again, check the balance factor for this. Where we are inserting everything on the left hand side. Right? We are inserting on the left hand side. Now observe 1. For this, the balance factor is 0. For this, the balance factor is 1. And for this, the balance factor is 2 minus 0 is nothing but 2. Again, it is not having the balance factor -1, 0 or 1. Okay. So that this tree is not balanced. Now, what we need to do? We need to again perform the rotation to make it balance. Now, what rotation we need to do? This is happening because of we are inserting this node on the left hand side. Because of this, there is imbalancing of tree. Now, what we need to do? We need to make, because of this LL It is imbalancing. Now what rotation we need to do? We need to do RR rotation. RR rotation to make it balance. When I am going to perform RR rotation, it will be pulled down, 3 will be pulled down, 2 will be on top and 1 will be on left of it. Now you can check this. Yes, now the tree is balanced. Here observe the names. Because of LL, it is imbalanced, so that we are going to perform the RR rotation. In the previous case also, because of RR, that is, we are going to insert the elements on the right hand side. Because of that, it is imbalancing. We are going to make the left rotation, right? Please be clear with this. Next, left-right rotation. Now you can see how this will be performed. Suppose you have given the elements of 3, 1, 2. Right? Construct a tree first. First node is 3, no problem. Balance factor is 0. Next, insert 1, where we need to insert 1. Inserting 1 on the left of this. Why? Because 1 is less than 3, right? Now check the balance factor. Yes, the balance factor for this is, this one is 0 and this is 1 minus 0 is nothing but 1. Up to now we don't have any problem. Next, I need to insert 2. Where I need to insert 2? 3, right? 2 is lesser than 3, so we need to go to a left subtree. And if I am going to check with 1, it is greater than 1. So I am going to insert here. Now check the balance factor for these nodes. For 2 it is 0. For 1 it is, this is 0 minus 1. So here also we don't have any problem. And when I am going to check with the root node, here we have 2 left hand side minus, we don't have the right subtree, so that it is 0. So we are going to get 2. Now it has to be balanced. With single rotation it is not possible to balance. Why? Because I have inserted this node, because of that it is imbalanced. Now observe, this is L and this is R. Right? Because of R inserting, this is imbalanced. Right? Now we need to perform the rotation. With single rotation, it is not going to get. So first we need to perform, because of this R it is imbalanced, first we need to perform the left rotation. When I am going to do the left rotation, just observe 3. If I am going to rotate this, we are going to get 2 here and 1 here. Right? 2 and 1 here. Now you can see still it is imbalanced, but we have performed which rotation? Left rotation. Left rotation first. And then we are going to perform another rotation also. If you can see here, this is completely LL. This is completely LL. Now which rotation we need to perform? We need to perform, because of this LL rotation, this is imbalanced, so we need to perform RL rotation. That is right rotation we need to perform to make it balanced. When I am going to perform right rotation, what you are going to get? 2, 1 and 3. 2, 1 and 3 is going to be getting after performing the right rotation. So the name of this one, we are going to name it as LR rotation. We are going to name this one as LR rotation. Okay. This is the one where we are going to perform in this left-right rotation. Because of LR, it is imbalanced. That's why we are going to perform left rotation first. Right? On this, we are going to perform the left rotation first, and then we are going to perform the right rotation. That's why we are naming this as LR rotation. Okay. Like this way, this will be balanced. Next. And here we have one more rotation that should be performed. That is RL rotation. That is right-left rotation. One case we have already seen. LR rotation already done. Right? Now suppose you have the case like this. Suppose you have 3, right? 3 is your root node, and let me take one more example, not 3. I need to get a tree like this. Suppose we are going to take one example related to 1 greater than 3 lesser than 2. Yes. Now take the elements in this way. Yes, let us consider the right left rotation, how we are going to perform. Yes, we have already seen the left right rotation here. Now we will be looking into another rotation, that is, to easy comparison I have placed this right left rotation. This is nothing but RL rotation. Okay, consider the elements 1, 3, 2. Suppose you have given the elements in this way. Now based on this, how we are going to construct a tree? The root node is 1. The balance factor for this is 0. If I want to insert 3, where I need to insert? It is greater than 1, so I need to insert on the right hand side. Now what is the balance factor for this? For 3 is 0, and for 1 is, this is 0 minus 1 is nothing but minus 1. And the next one we have is 2, where I need to insert 2. 1 is greater than 2, come this side. Greater than 3, we need to insert on the left of 3. Now check the balance factor. The balance factor for this one is 0, this one is 1, and this one we don't have the left subtree, so that 0 minus 2, that is nothing but minus 2, right? This is imbalanced. Now how this has been imbalanced? Because of RL. Because of RL, it is imbalanced. Now we need to perform the rotation. Double rotation we need to do. Why? Because we need to rotate this one first, this part first, and then we are going to rotate this. Now first, what is the rotation we are going to do? On L we need to perform the right rotation. On L we need to perform the right rotation like this. After performing right rotation, we are going to get the tree in this particular form. Still it is imbalanced. Now what I need to do? This is because of RR, it is imbalanced. Now we need to perform the left rotation, so that we are going to get 2, 1 and 3. This will be balanced like this. Now here in these two cases, this case and this case, we are going to perform the rotations double time, right? These are the 4 rotations that we'll be using in our AVL trees to balance our tree. And when you are going to see the AVL tree operations, here we are going to perform 3 operations: search, insertion and deletion. Searching is similarly as the BST, how we are going to search the element. Suppose if you have given some node with the 50, 45 and 40 and 60, you consider this is the one. This is the tree which you have given. How you are going to perform the searching? Suppose I want to search the element 40. The similar way in BST, how we are going to search? First search with the root node. Then it is lesser than 50. So that I need to go to the left subtree. Again search with 45. Is it the key node? No. So that we are going to move to the left part of it, and the element is found, the key element is found. If the element is not there, element not found. Like that way we are going to return. The same as BST, how we are going to perform. Next, we have insertion. This one is little bit different when we have seen with the BST. That one we will discuss in a separate session. And deletion is also similarly like our BST, but when you are going to perform the deletion, after deletion also we need to check for the rotations, whether the tree is balanced or not. If the tree is not balanced, again we need to rotate the tree, and the tree has to be balanced after deletion also. Okay, that one also we'll see later. After performing any of the rotations on AVL tree, the balance factor of every node must be checked. This has to be mandatorily done. After doing any of these operations, you have to do this. Balance factor has to be checked for each and every node. There are following two cases that must be possible for AVL trees. One is balancing, another one is imbalancing. If the balance factor, for the case 1, if the balance factor is 0 or 1 or -1, the AVL tree is said to be balanced. The operation is completed or closed. In case 2, if the balance factor is not a 0 or 1 or -1, in that case we can say it as imbalanced, and we need to perform the rotations on the balanced to make the tree balance. And these are few rules to be remembered when you are going to perform these AVL tree operations. One is, first rule, after inserting an element into the existing AVL tree, after already you have a tree, into that if I am going to insert a new node, in that particular case, first balance factor of only those node will be affected that lies on the path from the newly inserted node from the root node. Wherever you are inserting that node, from there you need to check whether the balance factor is affected, whether we are going to have the balance factor or not. If it is not, then we need to again perform the rotations. And rule 2, to check whether the AVL tree is still balanced or not after the insertion. After every insertion, we need to do that. There is no need to check the balance factor of every node, right? Check the balance factor only for those that lies on the path from the newly inserted node to the root node. No need to check for all the nodes. We need to check for the newly inserted node. That is enough. Based on that, we can say whether the tree is balanced or not. And rule 3. After inserting an element in the AVL tree, if the tree becomes imbalanced, then there exists one particular node in the tree by balancing which the entire tree becomes balanced automatically. Right? After inserting, we need to check is there any possibility of balancing tree, right? By automatically it can be balanced, that can be checked. To rebalance the tree, balance that particular node. Only that particular node can be balanced instead of changing the complete tree. To find that particular node, traverse the path from the newly inserted node to the root node. To do that, a particular node to be rotated or to make it balance, we need to traverse from the path from the newly inserted node to the root node. Where you have inserted the new node, from there to the root node, we need to take the path. Check the balance factor for each node that is encountered while traversing the path. Only that path we are going to verify. The first encountered imbalance node will be the node that needs to be balanced, right? From path to root node, when you are moving to find the balance factor, where you are going to get the imbalance of that value, from that value onwards, we need to balance the tree, right? To balance that node, count the 3 nodes in the direction of leaf node. How to do that? From the leaf node to the 3 nodes, we need to count, then use the concept of AVL tree rotations to rebalance the tree, right? This will be understanding when you are going to solve an example, okay? So that we will be seeing the example of this insertion in the next session, right? Now, what we have discussed in this session, we have seen about what is AVL tree, what are different AVL tree rotations. We have 2 types of rotations, single rotation and double rotation. In single, LL rotation and RR rotation we have seen, and in double rotation you have LR and RL rotation we have discussed. And we have seen some of the points when you are going to perform any of the operations like insertion, deletion and searching on AVL trees. These some of the rules you have to remember. I hope you understand this concept. Thank you.